record. It might all go to hell the moment I try to actually show you a window running inside of Visual Studio. That'll be the challenge there, I suppose. But we'll get there somehow. We'll make do. So there have been some issues still with regards to some of the people getting Sandbox running and so on. So I won't really give away the solution to the matrix transformation homework yet. But the fundamental part of the homework is, of course, there's 3 operations that we want to perform on a matrix to come up with a single transformation matrix. It combines a rotation, a translation, and a scaling. Right? So you want it with a single matrix that you can put into that set of numbers at the bottom, with the translation in the last column, just for orientation, you know that the translation's in the last column. And then you also need to modify the shaders to get the vertex shader to use the combination of the model view and projection, or projection view and model. You have to figure out what order they need to go in, to alter the orientation of the model and take into account the perspective or projective matrix and the view matrix. So you wind up with the appropriately kind of, it should be square. So no matter if you stretch the window or not, it should remain square. That's one thing, that having the view and the projection matrix included in there will make that work. Let me tempt fate, and just because sooner or later I got to try to do this anyway. And with this active, if I run this, let's see, put people on. Nobody's gonna be able to see that. Maybe you there. And I'm gonna try to create another capture source here. Yeah. So people online can kind of see this. This is a even more crazy version. Slightly more crazy version, where it's not just the offset, the automatic motion isn't just the set of triangles that form the quad. They aren't just bouncing side to side. In this case, it's actually doing an animated tumbling rotation. So let me fix that so that it'll be sort of like what you have to do in the homework, but not exactly. So that's the good news. Use what I do here today to kind of figure out how would I fix the homework if you haven't already. So the first thing is that this automatic tumbling rotation, we want to take a look at what's going on in the vertex shader to get it to kind of settle down. So you should begin to get kind of comfortable with what's going on in your vertex and fragment shaders. So there's some new stuff in here which we'll kind of ignore for just a moment, where you can see fragment position, frag pos, and normal, which is going to be helping us out with lighting later on, trying to figure out the actual location of a fragment and the actual normals to the surface here. We're not going to use those yet today, but what we're really interested in is mainly just this GL position, right? You'll see that in the shader that you have, the GL position. And you can see I have a combination of different matrices being used. Now I'm going to just drag or just take out this last one, this matrix 3. So you can see a PMAT, VMAT, and MMAT. And if I say use shaders, suddenly everything snaps and stops spinning around because it's now using this set of matrices down here. Right, or this matrix down here. I'm going to set it to 0, 0, so that there's no translation, there's no rotation, there's no scaling. Right, this is just a unit matrix there, one along the diagonal. Right, so there's no rotation, anything going on. To also get it to settle down a little bit, or at least to kind of make it look a little bit more like the version that you're used to, I'm going to take out some of this other code which is used for lighting. We'll get rid of that, and we will just use, if I look in here, let's see, fragment color determined by the texture. So say use that. Things aren't quite right yet. Frag color, texture. Oh, well, I have two lines, frag color and frag color. So I don't want the second one being used. I just want the first one being used. So now if I say use shaders, I get the RPI logo. We're back. The RPI is teal. Right. So I have the fragment color coming directly from a texture here, which is set up in the C++ program if you want to dig into that. And the important thing up here is that I have the position of the vertex, or each of the vertices, determined by the incoming APOS here, which is laid out up here. You can see it's in position 0. My VBO attribute 0 is the first one there. And then I am transforming that incoming vertex according to a P, M, and V matrix. All right? You normally call it an MVP, but it's actually this order is swapped here, P, M, P, V, and M. So that's a hint in terms of, as you're figuring out what this matrix is doing here, you have to sort of do things in an opposite, a backwards order, and it's kind of detailed in the homework description there. All right. So if I were to do things like move the model forward in the Z direction, I can kind of see it getting bigger because it's approaching the camera. Right? I can just move it easily. The easiest thing to do is check translations, right? Just scooch it over by 0.25, maybe drop it down by negative 0.25. Right? So I can move things around that way. If I wanted to scale it, we know that scale is the diagonal. Which one do you want to scale? Do you want to scale evenly? If you want to do basically what we call a rigid scaling. And if I don't lose my mouse. So if we would say 1.2, I'm going to get used to, I'm going to look at it on this screen. Can I do that? No. It's like a nightmare trying to control it on one screen there. I'll change this to 1.2. Let's square again. The Z is not going to have, scaling Z is not going to have much of an effect because right now we're just looking at it straight on, and it is a flat, it's a paper thin model, so scaling in the Z direction really doesn't do anything. Right? Even if you made Z 0, it doesn't do anything in the scale-wise, because it really is just a flat model for now. All right. So there's a bunch of other stuff going on we'll start talking about in here. When it comes to things like lighting and creating kind of subtle changes to surface appearance, that's all going to be kind of stuff we can take care of and provide in our shaders. Right? Lighting is going to be the first one that we start to tackle. We're actually going to start tackling lighting next week. The other big thing which we're going to need to do, and this will come into play on this next homework, so you can actually do this even with the version that you currently have. There's not going to be a new version for this homework, but the big thing you're going to do is, if you click this button and say swap texture, it toggles you between two textures, one being the RPI seal, and the other one being this built-in texture that you generate. And in that texture that you generate, you can say, you can scale it up a little bit more. Be careful. If we scale it too much, it then gets too close to the camera and it clips. We'll kind of center it. So what's being put in here is drawn the old-fashioned way, pixel at a time. And this demonstrates a couple of different algorithms that I'll talk about today, actually even in some bonus algorithms that will get thrown in for free. The three main ones being how to draw a line. We're going to look at, today we're going to look at three different methods, the kind of the brute force method, a DDA method, and Bresenham's line algorithm, which is one of the most popular ones, one of the most common ones, commonly used ones. We're also going to look at Bresenham's circle algorithm, which is how the circle is drawn. And we're going to look at cubic Bezier curves, which is what this one is up here, this actual curved part. and it's showing the lines. The blue line here represents straight lines of the control points of that Bezier curve and how the curve is generated. So the interesting part is this cubic curve here. So the next homework, everything is in place that you can build in a set of algorithms to do that, right? If you look it should be in basics.cpp. There's a bunch of just kind of empty shell kind of stuff in there. The main thing in there being that, let's see, now I'll have to temp fade again. And I guess I can move this for those of you who are online. How should I do this? I guess I'll just push it over to there. And for those of you in person, let's see, should I close the window? I guess, well, eventually I'm going to have to close this window anyway, so let's see if just the world crashes when this happens. First I'll say save shaders. So save shaders is going to save the current contents up here and save the contents of that matrix, just to remind you. Use just means use currently and doesn't save it, but save shaders saves it, swap it. So, all right, so close that window. So you're going to see, yours probably actually looks like this, which has not too much going on, a little bit of junk going on in here. And how elaborate we get is sort of up to you. But the main thing in here is that it has, at the beginning, you'll see these two lines that establish the dimension, the x and y dimension of the texture we're going to use, or we're going to create. And it's going to be a very simple buffer that's just an x and a y, so 2 dimensions, and 4 unsigned characters per position on there. So we're creating a frame buffer, or a texture buffer, right? Each location on there can have a red, green, blue, and alpha value, and it has an x and a y. So you can draw whatever you want. There's also something called write ppm. I think I include this in the version that you have. If not, I'll get you a version of this. It's a very, very primitive image file format, ppm, which is basically a byte for every byte in the buffer. Basically draws it kind of out. It has a very, very, very simple header, which just says p6 and the dimensions of the file. And then all of the pixels in there, in the image, are output red, green, and blue, one at a time, just throws it out. Now, how many of you, I assume this, but maybe it is a bad assumption, let me know, have done programs where you've done some kind of basic line input output get line or some kind of streaming, right? This shouldn't be totally new, because you'll need to do that, not in this homework, but the next homework after that. Whether or not we do this used to be critical when we didn't actually have the textures. We couldn't see them on the screen, but now we can, so it's good to know. There's all sorts of different file formats. This one doesn't do anything fancy. There's no compression. So it generates really, really big files, and it's just really ugly. And if you look through there, you can see some vestiges of basically a primitive graphics language, kind of created on the fly last semester. This kind of primitive version of a graphics language that had a way to set a translation, rotation, and a transformation. And so there'd be a way to transform a vector 3, which would be usually just a point, x, y, and 1. And you could set the translation for that one matrix. You could also set the rotation for that one built-in transform. And that could be used to do things like, let's see, I think down here, there's a little example where we'd set the translation, then draw a set of triangles, translate, draw a strip of triangles, rotate, draw that triangle strip again, rotate again, draw the triangle strip again. You may have remembered on the previous image there was a set of three things that kind of rotated there. It also had, where's Bezier curve? There's a Bezier curve up here, and this is the set of control points for that Bezier curve. So it had, typical Bezier curve has 4 control points. We'll see that in the lecture. So it would draw that, draw a whole bunch of random lines across all over the place. That other version didn't do that. And the one part it doesn't include is a draw circle. So you have to do the draw circle kind of from scratch. Important thing that it does have, of course, is things like how to draw a pixel. And drawing a pixel basically means putting that color into the array somewhere. Right? At its location, you put that pixel. So we have totally software-based rasterization of these models. So we have our own little simple programming, simple graphics language. For the homework, you wouldn't have to do the triangles and triangle strips. Leave that as sort of an extra credit piece. And if you can just draw lines, a circle, and a Bezier curve, those are going to be the parts for the homework. And we can kind of take it from there. So let's jump in to, let's see if I can get there again. All right. So yeah, let's talk about models and meshes, and that requires me to go to over here. Or actually, well, let's see. I guess we can go, we'll talk about the lines and curves first. I kind of had intended to do them the other way around, but why not? We'll do it this way. So line and curve drawing algorithms, the bottom line, pardon the pun, I can't help myself sometimes. You should know that by now. Everyone enjoys a good pun, right? Hopefully, maybe not. So this shouldn't be too much of a surprise to anyone. Equation of a line. Y equals mx plus c, sometimes it's y mx plus b. We'll use c because we like a's and b's for our subscripts on our 2 points, our beginning point and our end point for the line. All right, so this is pretty basic. M, of course, being the slope of the line, which we can figure out if we have any 2 points on the line. We just subtract the y's, gives us our dy. Subtract the 2 x's, we get our dx, and that gives us the slope. How fast the line is sort of changing y versus x, right? Pretty basic stuff. So let's think about that now, and how would we draw a line in a raster image? Right? Now we're going to talk about raster images, not trying to just specify 2 points and let hardware do it. So we're going to do it the chunky way with pixels. And that presents itself with some issues, of course, because we have fixed pixel locations. We can't just decide, okay, plug in a number, we get back some number, and plot that number. It can, if you try to do it completely naively, with simple geometry-based rasterization, it can sometimes lead to gaps and become rounding intensive, especially. Right? You're rounding every pixel every time you try to move something, you round it. Rounding is expensive. It used to be more expensive in terms of CPU usage. And you can imagine if you're trying to draw things like a nearly vertical line that goes almost straight up, but not quite. Right? It goes up in that direction. And x, normally you might say, okay, I'm going to be plugging in x to figure out y, but x might be changing in tiny little increments. So how do I figure out, from my x, how do I plug in a small enough increment to not create some big gap? Because if I put in x as 1, and it's down at the lower part, or the lower left part, sorry, everyone online, say a lower left part of the line, and then suddenly there's a big jump in the very next pixel, I'd wind up with just a line with a big gap in it. Right? So it's tough. If angles were all 45 degrees and everything always slope slowly in the y dimension, be a piece of cake. But we have issues. Now, we can, of course, just walk the line. We have to figure out, okay, in the normal case, like if it was a nice, smoothly, well, lines are always, of course, increasing smoothly. But they're increasing slowly enough so that maybe they're 45 degrees. Every time we moved one by x, we would move one by y, and it would all work out well. Or if the line was sloped low enough or pitched low enough that when we moved from x is 1 to x is 2, it would be near enough, then we wouldn't wind with a gap either, right? So we could say, okay, let's start at x1, move to x2, move to x is 3, x is 4, and so on, and calculate y, and it'll work out if it's not too steep. So we have that steep problem. So to fix that problem, we consider the slope of the line, and when we're traversing the line, when we're walking along the line, we want to move according to that more steep dimension, according to which one it is. And you basically decide, okay, do you solve for y or do you solve for x? Depending on what the slope of the line looks like. You know, is it greater than, is the magnitude or the slope, the difference of the magnitudes, right? We can figure out, is it pitched really high up or pitched, you know, really flatly, and then walk along whichever one makes sense and just kind of flip your equation. So if we wanted to figure out for the simple line, we would either be saying y equals mx plus c, or x equals, let's see, I didn't figure it out there. Here, x equals y minus c over m. We do one or the other. So our primitive line algorithms basically have two different cases. And ahead of time, we say, all right, well, calculate m, and if that magnitude of m is less than 1, meaning numerator is smaller, we do one or the other. Right? And then our calculation is pretty much what you think, just like our line, you know, we just solve here. Everything is in floating point. We just kind of figured out, so we, you know, move along. X increases one at a time because we have pixels here. Now, you may need to convert if you're, right? We're assuming here we're in the world of pixel coordinates. You know, every 1 is a pixel, 2 is a pixel, 2.5. Who knows what that is? The boundary between two pixels, but we're not going to worry about that. So in this case, we increment by x as we loop through, and as we move from the beginning, the starting the lines at xa, and we move all the way to xb, just pixel by pixel by pixel. And then we have this one step where we actually round. So every time it comes time to plot a pixel, we have to say round it, put it there. So we have this rounding, we have this multiplication here, and even in some situations you may wind up doing extra calculations you need to because you wind up on close borders and you wind up rounding to the same number and so on and so on. It's not the most efficient thing in the world, but it does work. Right? This is a simple line algorithm. This was quickly replaced in computer graphics because floating point arithmetic was so expensive. Nowadays, not as much, but still, when you want to optimize, and a lot of graphics cards actually don't use these methods because they want to be very fast. You want to do things as efficiently as possible. The idea came along to use something more incremental, something where we could avoid either a bunch of the multiplications or maybe avoid the rounding. The first thing that came along was a thing called digital differential analysis. That's the first line, one of the first line algorithms, first big ones. And the second one being Bresenham's line algorithm, which starts with that same idea and runs with it from there and kind of increases some efficiencies by making it all work in an integer space as opposed to needing floating point or needing any kind of rounding. So they're both what we call incremental line algorithms, meaning you have to go one pixel at a time. You can't just calculate a point on the line like you could with y equals mx plus b. So you have to generate the next pixel because you're always sort of adding some amount to the previous pixel. It's either its x value or its y value because it kind of works that same way. And then decides, okay, what side of some number are you on? And do you, do you plot the pixel or not? So here's the first take on that. And the thing in here, the way it figures out or it takes into account which is the greater of these two, it actually builds it into the equation. It doesn't make a decision based on which is the steeper gradient, but actually builds it into its increment that it uses. So it avoids that orientation step, or it bakes it into this calculation, I should say. So this comes along and it says, all right, well, we're going to create an increment to move along the axis, and we're going to scale it according to whichever one is bigger, so that everything scales down, and you can work in that smaller space. So we have an increment to add to x, an increment to add to y, and then we can move from pixel to pixel according to the increment, setting pixels as we go. Right? So we still have to round because this is floating point, because these values here we calculated them ahead of time, but they are not integers. Right? We can't count on those being integer at all. So we're still in floating point largely, but we've avoided continuously calculating the line, but we still wind up with this rounding problem. So the first DDA moved us a little bit closer in that direction, have the notion of being at a pixel and then keep moving along the line, but we still have issues. After that, Resonan came along. This is just, one of the pillars of computer graphics, I suppose. Removing the need to round and making it all work in just integer position. And the way it works is that you are basically maintaining a target threshold that's 0, that as you move in between pixels, as you're drawing pixels in according to orientation, you're going to cross that threshold, meaning you need to move up 1 pixel, or you don't cross that threshold, meaning you just continue kind of moving the way that you're moving it. Right? So imagine if we're flat, we're kind of like always adding a certain amount, saying, okay, did I cross, did I cross, did I cross? And the moment I cross, then, okay, I can move up by 1. Right? So once we cross, we adjust the increment back by the opposing increment. So we'll see this in the calculation. I think it winds up looking a little more obvious. So you're continuously comparing to 0 and seeing, are you crossing this threshold? Which side of the threshold are you on? The moment you become positive, you know it's time to move. As long as you're negative, nothing changes. Then you pop up 1. Then you know you need to adjust again to see, okay, because you always want to compare to 0. It makes it easier than trying to continuously figure out what the threshold is. You just always compare to 0. And what seems like an obvious thing after you start figuring it out is that since we're only rounding by halves, you're either close to 1 pixel or the other, that means we can do everything just in terms of halves and multiply everything by 2 ahead of time, so we can say, okay, are we 1, are we 2, are we 0, are we 1? We know, is it time to draw? So we don't have to worry about the rounding anymore because of that. It does, however, we do need to figure out what orientation we're in, though. And here's just sort of a coded in. It's pretty close to C++ code. It was meant to be pseudocode, but it's pretty close to C++ code. So once you figure out your magnitude of m there, or excuse me, your absolute value of m there, you can decide to do, am I moving a single, here, along the x direction. Right? So in this while loop, if we look, we basically start off saying, okay, plot what would be the first pixel, right? X starts off, x and y are a here. So you plot our first pixel, assume we're going to move by x, assume we're going to move by x, and now we're saying, okay, in the time we moved x, y would have moved by a certain amount that's scaled. We say, okay, does it cross that threshold? Does it move us up 1 pixel? If it doesn't, we just go on and continue moving along x. So we'll plot, plot, plot. the moment we cross the threshold, then, all right, now we pop up y, and we reset our threshold and figure out, keep going through. And we wind up moving across until we've gone from the lowest x pixel to the highest x pixel, move along the whole line. The opposite approach, very, very similar, except basically we have some, some of the y's and x's swapped here. Right? We're moving along one y at a time so we know we can move, a little bit, a little bit, a little bit. When is the time to move one direction or the other? Right. So those wind up being our fast line algorithms. A lot of systems still use those. Right? So at the end of the day, somewhere in your graphics card is deciding, okay, I have to figure out where on the screen it is, where's this line that I'm drawing. By the time your fragment shader is calling, it may have already used this algorithm to figure out how to connect points to other points. One of the other algorithms, there's a bunch of them, President Hemp just kind of went to town on creating graphics algorithms back in his day, was his circle algorithm. You can see all about optimizing operations here. And one of the main optimizations in his circle algorithm, as well as what's commonly known as the midpoint algorithm, is someone had to realize this for the first time. Someone had to say, well, you know what? If I need to draw a circle, octants of the circle have a lot in common. Right? So imagine, if you calculate the curve or the pixels in this octant here, you can do some simple things based on the radius of the circle to move, take that same value and just move it down to here, to here, to here, and kind of repeat it all the way around the circle. So instead of having to calculate pixel by pixel by pixel all the way around the circle, you basically calculate one octant and plot 8 pixels for every pixel that you would have calculated here. Right? 1 plus 7, right? So let's plus the 7 also. And the way that it figures out how to draw at that radius, depending on, because we can't calculate exactly, again, because, sine and cosine and so on, avoid floating point if we can, is we can figure out in brute force to say, all right, given the radius, we know 1 pixel beyond the radius and 1 pixel short of the radius. We compare as we move along. We start moving, say, at this location here. So we say, okay, x is so-and-so. There's no y yet. And we can compare that to say, did we cross the distance at our radius? And then we move up or not. And we're always kind of comparing, similar to line algorithm, we're going to be comparing to this difference between the radius and our actual value to figure out what side of the circle are we on? Are we inside the circle, outside the circle, or on the circle, so we know what pixels, which pixels to set. Right. And this is, in a nutshell, what that algorithm looks like. Right. So we use the radius and 1 minus the radius, and then continuously compare again against that, that threshold, and adjust the threshold as we move around this circle, knowing the different ratios that are involved. So there's a little bit of magic number in here that is basically 3 and 5. I did a little bit of optimization here. I gotta just wipe my nose. Too much humidity in my mask here. So some of these, there's all sorts of ways to, once you have the basic algorithm, you can always decide to optimize a little bit. I tend to, my style is to sort of optimize out. If you look in certain textbooks, it'll have if p is greater than 0, and then if p is less than or equal to 0, have a whole separate case for that. And most of the stuff that happens in the p is less than or equal to 0 is this part down here, which really happens in either case. So I like to eliminate else's when I can. That's my personal style. So you might see some of my code where I'm eliminating else's, but functionally it's the same thing as kind of drawing the whole thing out, if you like. So this is how you do that, and then this is the part where how do you plot the ADT? And it's really just saying, okay, given the center of the circle and the calculated point that you want to calculate, then what that relationship is depending on what octant you're in. Now, the fanciest algorithm we'll talk about today, and in the end it kind of works out to be one of the simplest ones, is Bezier curves. It sounds really, really fancy. It's got a cool French name. It was invented by Pierre Bezier, during the 60s for designing curves for the bodywork of Renault cars. So they wanted to basically say, okay, how do we model these things? How can we have, create these really interesting curves on a computer that we're not having to figure out what the actual formulas are, what the actual curves are. How can we specify just a certain few points that we can control and move around and create these interesting curves parametrically? And Bezier came up with this way. It's basically from 4 points, you set 4 control points, and it'll create this nice parabolic curve in between them, depending on where they're positioned. And you also can kind of link them together to create these kind of wonderful curves. So it all came out of automotive design. Since then, it's been used for all sorts of things: computer fonts, animation, even motion curves. If you want things to move along a certain path and you want to come close to something and then avoid it because it's trying to hit certain things but not actually, actually touch things, perhaps. You can combine them into splines, generalizing the higher dimensions to form surfaces. So you see sometimes cool parametric surfaces, terrain generation, all that sort of stuff. A lot of that is based on the same kind of parametric curve generation. And let's see if this, yeah, cool, my animation's working. It's largely similar to, we're all familiar with lerping, right? If you want to go between 0 and 1, you want to interpolate between one value and another. So Bezier curves is not exactly your simple lerping, but it has definitely a commonality with it. You'll see as it's moving through the or along this path from 0 to 1, calculate here, you see t changing. It's basically weighting the contribution of each of the control points. So as it moves, and eventually when it hits the final one, the final point is what hits. Right? So you notice the 2 outer points are always hit. The 2 inner points are pretty much never hit. Maybe you could come up with a version that might hit them, but generally they don't hit. And it uses a set of basis functions to figure out the contribution of each of those. Right? So it's not just a linear interpolation. It's based on these basic functions here, these 4. If you look through the presentation, you see blue, green, red, and cyan. And they do look an awful lot like linear interpolation or easing in and easing out sort of thing. So imagine combining linear interpolation, easing in and out, this version here. The implementation looks a lot also like kind of traversing or doing a lerp sort of thing. So you start at one point, and this is I don't know if I can name this one after myself. This is my particular implementation to come up with it's an interesting optimization. Spline Bezier curves don't necessarily plot every pixel in between them, right? They're based on U and they're based on interpolation. So you can choose how coarse you want them. What increment does U move along? U is a floating point number. It has to go from 0 to 1. I haven't seen an integer-based Bezier curve at this point. What I decided to do in my implementation that I showed before in that texture mapping demo there is every point that is generated as you vary U, and in this case we're varying U by an eighth, right? So we're 0, eighth, quarter, 3/8, and so on as we move through. So a few points that we're at. We actually draw a line in between those points instead of um, just drawing the points, right? So we can combine, say, Bresenham's line algorithm with Bezier to kind of give us a nicer approximation with fewer intervals if we want. Okay. So this is definitely pseudocode. You have to figure out, I didn't give you what this basis function is, but it's basically, from here. Right? So when it comes time, compare these basis functions, you're going to need to use those in here. And you'll see each of the control points making its contribution according to that basis function, according to that, where it is at that slope in time, or that moment in time. Right? So U starts at 0, moves its way towards 1, and we just plug in the basis function according and multiply that by our x value or our y value. We just get the result. And here's my big contribution. Say, well, okay, draw a line in between them, but the one thing you have to do is say, well, okay, the first point that I get, I can't draw a line between one point. So we wait until every other one. So the second point, when we're not 0, we're not at the very start. From then on, we draw from the last point we came up with to the point we just calculated. Right? So we wind up creating segments as we go along. So that's a quick Bezier curve. And that is your reference. Feel free to look at other references as well. But now in there you have Bezier curve, a circle drawing algorithm, and you can choose from the DDA or the Bresenham. Recommend the Bresenham just because it's a classic. So it's up on Elements for your reference in there. If you want to use the basics.cpp that's there, probably a mishmash of all kinds of different lines. If you want to just draw a certain few lines, I can give you I'll give you a set of specific numbers to do so that you'll wind up with an image that looks like that we'll all have the same image to kind of refer to. And then from there, with those simple algorithms, you can kind of do all sorts of things. Like you saw, I started creating triangles and triangle meshes and strips and so on, just saying, okay, I get a set of vertices and I connect them. How are they organized? Well, if there's a triangle strip, just like OpenGL, every time I get a third, I get 0, 1, 2, okay, I can draw a triangle. 3, okay, now I can use 1 and 2, and the next one, get a triangle, and kind of traverse the whole thing. All right, so you can create your own software rasterizer, your own software version of OpenGL if you want it entirely. A little crazy, but if you want to also go from there and get fancier, you can do things like fill, if you want to create a fill algorithm, flood fills, gradient fills, all that kind of cool stuff. Start from there and work your way up. Okay, so that's that portion of today. And let's go back to the other portion of today. So ultimately, the first project you're going to do, I'm going to simplify it quite a bit. And we want to basically create a 3D scene. We want to have some kind of scene, so I'll put some more parameters on there. And we want to create your own unique scene using all the techniques that we're going to discuss through next week. Next week we're going to start talking about lighting. So you're going to want to be able to sort of generate a model, right, which is, we can say, okay, what's the formula for a sphere? Has some pointers and things in it. We're going to show a sphere, a torus, and there's lots and lots of other algorithms out there. If you want to find, I know you're going to be able to find OpenGL sphere. You're going to do it. I'll just point you at a couple of them. It's going to be about the implementation. So you're going to include a geometric generated model as well as a loaded model, and you can use the technique that we're going to learn now. There won't specifically be a homework on creating your OBJ parser because you can either do this one or you can choose to do what's in some ways the more advanced version, which is what what's done on the Learn OpenGL site, which is to use the asset importer library. Although it provides code for that, I would consider just following that and getting it to work and getting the right files and everything can be more challenging than finding just doing the simple OBJ conversion. So your choice, and then be part of your project, right? So you have a simple scene that will have some generated objects and some loaded objects in your scene with lighting. Pretty straightforward, right? Everyone should wind up having a unique scene. How fancy you want to get in there. Oh, and some aspect of it should wind up being animated. We'll talk about some different techniques as we get into the lighting on that as well. So, 3D models. They can be built procedurally, right? Geometrically, we know what primitives look like. We know how to form platonic solids. You want a 20-sided die. You'd be surprised how many people decide to make every die that Dungeons & Dragons uses as part of their projects. Lots and lots of great equations and things out there for that. Or you can build models externally and have some method of importing them into your program, right, using them. Lots and lots of different ways to do that. I'll provide some so you don't have to create your own models. We're going to use, you're probably going to want to use one of two formats as we get to there, but we'll talk about that in a second. So, procedural modeling example. Okay, imagine building a sphere. Right? We know the equation of a circle. We can build it all based on there. Right? We start off saying, okay, well, let's have a circle, and then let's generate the z dimension or the opposite according to we have a circle in one face and a circle from the top. So we can sweep the circle around if we wanted to, creating these kind of sets of circles, and it's all about connecting the points. Right? So we create this wireframe, and how do we connect the wires? Ultimately, we want to create triangles, right? Group vertices into triangles. There are ways to use quads. We don't want to use quads. We always want to use triangles. Right? Always, always, always use triangles. The easiest thing to usually do is imagine, in this case, we're talking about uniform geometries. They're not optimized. Right? So every strip around, you'll notice that they become denser and denser as they get towards the top. So this is, like I said, probably not the most optimized thing in the world. You can want a really dense bunch of triangles at the top, but that's okay. And ultimately, it's a matter of kind of stepping through the geometry and creating two triangles for every kind of quad that you created. It's a natural thing to create quads because the uniform density x and the subdivision, it's subdividing evenly there. Right? Now, if you want to texture those, if you want to put a texture on a model, you need to, of course, select your texture coordinates. And that part is pretty straightforward as well. Right? You just, in the case if you want to stretch your whole model across, that's the easiest way. You stretch your whole texture across. That's the easiest approach. Where you're just varying the texture as it goes around from 0 all the way to if it's to the size of 1. This is something that actually kicked my butt for a couple of days because I was trying to do two things and not realizing I was optimizing myself as a whole. With 3D models, quite often we like to create what we call our watertight models, right? So that imagine we're creating this circle or this sphere, and at some point there's a seam that you hit, and I guess in the sphere case, you wouldn't necessarily, sphere, you don't. It's a donut model. So in this case, it's easy enough to say, okay, 0 is on one side and 1 is up here, right? And it vanishes into that 1, and it vanishes into the 0, and everything else is just stretched around. Well, no, I guess you do run into potentially into the issue, which is at some point, if you're generating something, you wrap back around again. And you have to say, well, okay, the vertex that I hit, and have that people on a line, but imagine you just draw a circle, and at some point you draw it back to yourself, and you divide that into segments, and you have 0 to 1. And you say, okay, it was 0 and 0.125, 0.25, 0.375, in the end, do you decide to make it watertight by joining this location, 0.875, to 0? Right? Because this was index number 0. This was index number 1, index number 2, index number 3, all the way around like we had in our models. Do you join it to itself, or do you create a non-watertight version, in which case you have something that's hopefully at the same location, maybe it is, maybe it's not, but it's at 1.0, right, as it goes all the way around. Because 1.0 and 0 in the case of a circle, or in the case of these sort of calculations, wind up being at the same location. Why is that an issue? Well, for watertight models, it's great to avoid that extra one and just have it join back to itself. However, when you're texturing, it runs into a potential problem, because the question is, this last bit here, what part of the texture does it use? And if it's going from 0.875 to 0, that's in one direction texture, versus if it's going from 0.875 to 0 in one texture, another tiny little slice that would potentially complete the whole image. So it's something to be careful or wary of. You see these like sort of special cases for textured models versus solid watertight models. It's a subtle point. As you see the torus, I'll talk a little bit more about that one. But that's kind of something to keep in mind as you see some of these models. Now, those are the things we've talked about so far. We've talked about in the other lectures about the coordinates, our texture coordinates. We even talked about colors of the vertices. We're going to introduce another thing that we've probably talked a little bit about, but we haven't really used them yet. Normal vectors. Right? What a normal vector is, it's a vector pointing out from that vertex. Right? Which basically tells us what direction that vertex is facing. Right? So in the case of a sphere, you can imagine that the normal is the direction vector that would be formed by just pointing from the center of the sphere to that point. Right? Since it's a pure direction, we don't care where it starts, but just that is the direction it points in. Right? So in the case of the image here, you see the red vector there. That red is indicating that that point faces out. Right? So we know which way that point is facing. So this comes in really, really handy when it comes to generating normals for models. Right? I say, oh, I need to store it. My name is just generate. Point to the center of the model and point out, that'll give me the vertex normal. You might think that. However, let's think of a cube for a moment. So a cube has corners, and if we try to draw a line from the corner of the cube where the vertices are from any corner to the center out, we wind up with these diagonals pointing out. So we don't get any normal that is a face normal. Right? Normally, pardon that one. In a lot of cases, you're going to want to also use potentially what are the normals of the faces, because those are the things that ultimately wind up being shaded or drawn or so on. Right? So for some type of models, it's going to be important to design the orientation with the idea in mind that yes, this isn't a smooth model. It might have corners. So in those cases, we have to have how are things kind of treated. So for now, when you're in the case of generating things like spheres and things that are generally thought of as being smooth, it's easy enough to calculate this normal vector by going from the center out. And you can do things like combine normals to kind of generate the in-betweens, or calculate normals on the fly if you know something about the geometry of the surface. Right? If you're going to calculate a surface normal, then you do things like take the cross product of the actual edges of the polygon, for example. So, back to our sphere that we're creating. The other part of creating a sphere, and you have your options on here. Again, if you want to get really, really sophisticated and figure out, there's a good case for using indices, right? Because we can generate all the vertexes, all the vertices for our sphere as one pass, which is what happened in this one, right? So we have slice 0, which is all the vertices around that sphere, and then moves up by 1, all the vertices around that one, moves up by another, all the vertices around there, right? Just moves its way around. You can come up with an algorithm that will create the indices according to, basically the number of slices and the number of segments that you carve things into. So you can, after the fact, generate the index list to generate your triangles. This is a common technique also. Generate all the vertices and then go back and figure out from there what the indices are involved. Right. So this is basically the algorithm. It's for each horizontal slice, I ranging from 0 through the number of slices in the sphere, and then for each vertex in the slice, 0 through the number of vertices, build two triangles out of a neighborhood of vertices above and to the right of vertex J. So this allows you to just create that set of indices so that you can group the vertices together. And here, because I know you all know how to use the internet, I'll just save you the one step. This is a really good step-by-step tutorial going through OpenGL and spheres. Song Ho, he's got a bunch of different, I think I should apologize, they have a bunch of different tutorials and algorithms and all sorts of things. The sphere is a good one. If you want to, just generate your own sphere, check out that page. Easy enough to do. Slightly more complex geometry, if you want to tackle this one, is the torus or the donut. Classic computer graphics kind of trope. And it's similar to the idea of a sphere, but instead of rotating around, you're just rotating around 0 and just creating a similar rotation each orientation. You offset the ring that you create, and then you rotate it around the origin. So imagine creating, here's 0, you have an inner radius, then you create the circle, and then you sweep it around according to the number of segments that you want. Right? And similarly, then you can go through the idea, pretty similar when it comes to creating the indices. You're just going around ring by ring by ring, and you just wind up going around it as opposed to just hitting the top. Right? This is a fun one. So if you decide eventually that you want to do spheres or you want to do something, in your project that, if you're going for a job in computer graphics some days, someone will expect you to have a torus in your quiver of things. Right. So in the previous versions of the course, this is where we kind of dive in, because some of the simpler models and things where we're just using triangles, you didn't really need to use the indices, but we kind of covered them a little bit more this semester earlier on, trying to draw elements from the get-go. But it's worth kind of remembering as now you're going to be hopefully creating your own algorithm instead of just using, or creating your own code instead of just using the sandbox as is. You have your vertices in a standard VBO, a GL array buffer. You have your indices in a GL element array buffer, which is different type of buffer, right? So you're going to have always at least 2 VBOs if you're using an indexed. One, if you're not using this, if you're just using GL draw triangles or draw array. But if you're using GL draw elements, you're going to have at least 2 VBOs, one which has the vertex attributes, and the other which has the indices. Now you'll notice here, this is VBO0, and the indices they have in VBO3. Why? Well, the style that the text chose, the old text chose, was to keep things like vertex coordinates, normals, colors, textures, texture coordinates, all separate in their own VBOs, as opposed to OpenGL, Learn OpenGL, and the Sandbox, where we're usually integrating using a single VBO and having it, each of the things kind of together. Your choice, right? And then at the end, it's a matter of binding which buffer is bound to the GL element array buffer and then calling draw elements. So the nice thing is you can potentially, if you want to just change that element array buffer because it's slightly different triangles that you're using that use this thing, that reference the same vertices. I don't know how often that occurs, but you can do that. Right. The VBO, there should only be one GL element array buffer kind of in flight at any one particular time. So in your VAO, one of them is going to be bound, and that's going to be the one that it automatically knows how to use the indices, right? OpenGL automatically is not necessary to declare anything about it, like to say, oh, it's attributes. You instead attribute pointers and things for that. You've seen that. Right. Similarly, we can certainly texture around it. We run into that, potentially run into that one weird thing. I already deleted the version that I had, or deleted the version that was wrong because it just frustrated me so much. Let's actually take a look at what this looks like here. Alt-tab, Visual Studio back in. Now, a little bit about how I attack this in the sandbox and what you might want to do as you're getting into things. So the way the sandbox is organized, the first thing I want to look at is just main down here. So in main, we set up our window hints and things for GLFW, so this is our basic setup. Some people were asking about, right now it requires basically OpenGL 3.3. Right? We're not doing anything, I'm not using any vertex or geometry shaders or a tessellation shader, anything really, really crazy and that stuff. So 3.3 is fine as far as this stuff goes. So that's what is happening here. Normally you tell GLFW kind of what version of things, you kind of hint at it, what profile of OpenGL you're using. It creates a GLFW window. Normally the GLFW stuff is all kind of the abstraction for the operating system, open up a window, that sort of thing. We set the frame buffers, and so on, so we have a context set up. And then there's this glad load GL loader. I've provided a pre-configured version of glad for you. Right? Glad or glue or glut, there's a bunch of different versions that are basically there to allow you to sort of abstract and make sure that you can just call OpenGL without worrying about, is there an NVIDIA card, is it an ATI card, is it a Matrox card, is it whatever. Each of them kind of set up for that, and just different people have implemented it. You should check out Google Glad OpenGL, and you'll find you can actually download a new version. And the way it does it is there's a web page that you go to and say, okay, what features of OpenGL do I want to use potentially? And you select, what profiles and so on, and it sends you a correctly built version that you can then use. I made a version that just had sort of everything built in for this, so we also have that. All right. And then there's some more setup. And as I've been implementing things, whether it's the triangles or quads or cubes or models, torus, whatever, I just have a little setup stage here. So if you determine that you want to add a sphere or another model or something, you can add that. That's how I'm always like kind of turning things on and off by brute force here. And I'm just going to turn on my torus. So that will generate the torus, create the VBOs, and it will create a VAO specifically for it. And then in my main loop here is where, at this point, after setting the matrices, telling it about the uniform variables, down in here is where things actually get drawn. And it's set up so that you could have multiple VAOs set up. You can have multiple models. You can actually have multiple metrics, each one with their own VAO, and that VAO will have VBOs associated with it and so on. So that's how why this is a little array of VAOs that it just cycles through, and every time you use one, it just increments, keeps track of it for you. A little bit of housekeeping is necessary to determine, is it using elements versus using draw arrays, but moving more and more away towards not using this draw arrays. So let me just compile that, let that run so you can see the torus. And let's see if it'll do the right thing. There. And get that there. So this is using, again, that RPI seal, or you could even, if my mouse is working, swap the texture and see the other one. And I will even sort of re-enable here. I can always, right now I'm just using the model matrix, but I'm going to go ahead and calculate or put in that 3, put that as part of my my transformation, rotate that around, swap the texture back in. And something, you start to see something is a little bit weird going on here. I think I have the culling wrong, or at least when I generated the model. Why did I never notice it that way? Oh, I know. That's because that was weird. I had it scaling the z to 0, so it's sort of collapsing on itself. That's another fun one. Not 11. Right. So this is the classic donut. And if I enable 2 things, well, we get bogged down. I'm going to stop that. And got this for everybody online. Okay. So you wanted to find, you can use, there's a couple of different torus. Oh, I remember what my point in the last one. I actually did a different, in that one I used a different torus algorithm. Instead of going like drawing a circle and sweeping around the normal, the way that I described there, it actually would draw it around the top and then sweep it around underneath. So there's not just, there's always like at least two different ways if you want to, sweep around, the smaller, create the tube versus kind of create a circle and then wrap it around and, create the torus from a larger circle that swings around and fills in the opposite direction. So, fun different ways to do it. All right. So, externally produced models. For the example here, they're showing the Blender application. You can export models from Blender in all sorts of different formats. OBJ is the one we're going to talk about. That space shuttle that I showed earlier on today was also created in Blender as an OBJ file. I think it was, actually I'm not sure it was in Blender, but it's also an OBJ file. So you can imagine how important it is to have some sort of model format, right? Where it's some way, you want to create everything as code and so on. So there's lots and lots of different file formats. OBJ is one of the simpler ones. If you want to, instead of an OBJ or building a simp, you can also do things like, read an STL file. So, things that are created for 3D printing, that's yet another file format. OBJ is a good one because it includes texture coordinates and normal vectors, usually includes textures and normal vectors as well. And it's a simple file format. You want to look for, I think they're all text-based. If you open an OBJ file in Notepad, you'll see a small header at the top, usually just what created it, a name for that file, or a name for this particular object called pyramid. So we have the first object, and you could even create multiple meshes or multiple models in the same OBJ file, but I think most of them just use a single one. So here you have a simple pyramid. And then line by line in the file, it basically gives us the attributes of each vertex, right? Or a list of attributes for vertices. So first off in here, and in the file, they can actually be interleaved in any way, shape, or form they like. It's pretty typical, though, to have like all the vertex locations first. So it's just going to be an X, a Y, and a Z value after a V. And you want to be careful. I've seen ones that have one space here versus having two spaces there, having different spaces in between. So as you create a parser, you want to be careful about avoiding things like that. So here it says there are 1, 2, 3, 4, 5 vertices, or there's 5 locations there. Right? Then we have a set of texture coordinates, VT for texture coordinates, and might be any number of those. And we would then have a set of normal vectors up to some number, right? It doesn't really resolve. We don't know exactly how many we reach until we get down here, which is a little bit wacky in certain ways. After all the coordinates, locations, texture coordinates, normals are specified one at a time, then it turns them into faces. You can have triangle faces, you can have n-gons, you can have quads, and so on. So be careful if you do create your own OBJ file. Depending on what the settings were for the tool, you can wind up having these quads, all kinds of crazy things. We like to have normal triangle faces. They're easy to deal with. And so what a triangle face is, see the line is prefixed by F, and it gives us a set of 3 indices to define that vertex. So for example, this first set of indices is the second, and it's not 0, so it's actually 1, 2, 3, 4, so on. So if you're looking up an array, you have to bear that in mind. So it says the second location, the first texture coordinate, and the first normal. That forms that vertex. The next one has the third vertex location, the second texture coordinate and the first vector normal. Right? Some files, you'll see they're really super easy. The simplest ones will be like 111, 222, 333. 333 or 222, 333, 444. You know, what a triangle script would look like. And they'll sort of just specify you get one of everything. The more elaborate ones will start to do this sort of thing. So it often involves a little bit of extra translation to go from this to even OpenGL, because OpenGL is only a one index, you know, a vertex has to have all of its attributes. Right? There's no way to say, oh, this vertex uses this coordinate and this, you know, it doesn't have a separate set of indices for each of these things. The OBJ file makes it a little bit crazy. What can make that easier to deal with, sometimes it means loading all of these things in. Just say you took a vector, you create a vector of all your vertex locations, a vector that contains all of your texture coordinates, a vector that contains all of your normal vectors, and then you parse through the faces and you generate, and sometimes it means being a little bit more verbose, to generate a vertex that combines these three things into a location and becomes index number one. When it then takes these, that is now vertex index number two. Right? So they potentially have all the same things. And there's some, you can get into optimizations and so on. But yeah. It's kind of what this is hinting at. Usually you abstract this sort of thing. If you look at a simp, they abstract their library quite a bit more, because it does a lot more things than, you know, this recommended simple object loader, where you say, okay, you should have some ability to say, open the file. And then typically after that, you would say, okay, give me all the vertices, give me all the texture coordinates, give me all the normals from those files, and then decide, all right, how am I going to parse them into the VBOs, right? So there's usually some number of different steps along the way. Yeah, they use a set where they look up in here, after they load into three of those, then they load the actual positions, value, texture coordinates, and normal vectors into that other second set. So I'll provide this model for you if you want to try things out. It's kind of interesting. I always find it interesting to see, you know, what the flattened out textures look like on here. This one's pretty straightforward. Now, if you want to get much fancier, and these provide all sorts of features that we're in no way ready to deal with just yet, using a simp or ASIMP or asset importer library supports a lot more than just OBJ files. You can import all sorts of different models. I like to use FBX files. They're a very common format, and they're very extensive. You can do things like, you know, embedded textures in them, have materials, have skeletons, have animations. So they're really complete and interesting there. This is one from the Mixamo website. It's a fully textured character, and it's animated. It has a skeleton. It uses skin deformation, all sorts of really cool things that you can implement if you like. The hierarchy within a simp is quite more complex and interesting. You can have scenes with multiple meshes, with multiple models. Each of those things, so we start with here having a scene, and that can either directly contain a mesh with materials and faces, or can have a root node that contains children nodes that wind up pointing back to particular meshes that point to particular faces, and so on and so on. You can have shared materials. So it's a much more elaborate and powerful hierarchy, and it'll do this for like a whole bunch of different different 3D file formats. I think it'll, including OBJ files. I think you can do that as well. So that brings us sort of the it for the week. So for now, like I said, the next thing in the homework is really to look at just some of the simple line algorithms. And let's see, as we talk about lighting, the thing, just a brief introduction to lighting, and then we'll end a little bit early today. In order to do lighting, of course, you have to say, well, how does, in all forms of lighting, especially in shaders and so on, we're going to do it, go through a bunch of different models. It's all about how light hits a surface, and it's going to depend on where the light is, where the camera is, where the viewer is, where the surface is, what the orientation of the surface, does light bounce off of it, and so on and so on. So we have to have models that have normals in there to really do anything interesting with them. That's why I like to talk a little bit about generating models and the relationship of the normals and so on. What'll probably happen, I'm going to kind of stretch out. I'm trying to basically kind of combine the homework and project one a little bit more and let the homework be a little bit deeper, but play into that because we'll want to have some of the lighting stuff available. We'll work that out next week. So next homework will get more intense after. Like this one should hopefully be a matter of look at the algorithms in here, draw some circles, draw some lines, and so on. If you blow through that really quickly and want to start thinking about object loading or generating models, by all means do that. But there won't be anything due next week with regards, certainly with regards to object models and or any type of meshes and so on. But if you do have the time, I would recommend taking a look at that. And some of the stuff, if you are following along on the Learn OpenGL, where are we? Thought I had it up there. Maybe not. So we're now definitely all the way through here. Right? We've created windows, created simple triangles. We should be able to write our own text, our own shaders, loaded textures. There's examples of that in the sandbox. Right? The sandbox should get you entirely through here, basically with examples of everything. The one thing that it doesn't have is creating models, generating sphere, and so on. And then we're also going to cover, well, we covered colors a little bit, not color lighting though. And these two portions as well. So that'll get us through for everything we're going to need for the first project, and likely, any coursework that we'll need to do. Everything else is really going to start to play into the next project, doing something more advanced. So if you are looking for examples, make sure you've got to go through things. I expect you to be familiar with all those techniques, whether you looked at them and really kind of analyze them inside the sandbox, or if you wanted to do it from scratch and follow step by step, compare them, look at the lecture notes, or kind of go through that set. So this is really, like I said, that's what we're responsible for so far. Right? So you've got a couple of different choices where you're drawing your materials from, or drawing your own exercises from there. Right? Any questions on that? Right. So like I said, the main homework thing, assignment is implement a Bresenham's circle, Bresenham's line, and the Bezier curve as per the lecture notes, which are already posted. And the framework to do that is in the sandbox. Should we do that? Okay. That'll be that. Have a great week. Unless there's, yeah.
So we got like
whole other homework result from the introduction. You should make this one. Yeah. Could we expect that to express other texture or swap textures in CSS? That's exactly, that texture world is drawn inside a basic.cpp. So go in here and comment out a texture world if you like. Sorry, and comment out the texture world first. And then you can comment out as much of that as you like, as much of basic.cpp as you like. Kind of start from scratch. Everything's there just as sort of for archaeology and forensic kind of purposes. All right. Everybody online got all that? Are folks still online?
Yeah.
Okay. All right. Well, we'll see you next week. Yeah, so next week will be normal. The week after that, I will be away. I'll provide a bunch of extra stuff, and it largely will be time to start working on your first big project as well. So it'll be less, probably not much new materials at that time anyway. So it'll be sort of studio week for that. All right. Thanks.
Okay. Thank you.